Hello, welcome to Historical Geology. I'm Professor Dooley, and this is a very brief introduction of Chapter 1 from the Stanley Earth System History textbook. So, Earth system history, really what we're talking about here is the interconnectedness between the biological world and the physical world, between the organisms that are living on it and the Earth itself. And what you'll find is that not only has biological life changed over the course of the history of the Earth, so too has the Earth itself. So hopefully by the end of this chapter, or really by the end of next week, you should be able to talk about these three main driving questions. So take a moment to look over these and then advance the slide. When we talk about Earth systems history, really looking at how to learn to use the Earth as a library. The Earth itself has a record of just about everything that has happened on the planet. And in the study of geology, what we do is learn how to interpret the books in that library, how to interpret what the rocks can tell us. And that's what we'll dive into pretty deeply next week, the following week, and within about 3 weeks, we'll be actually looking at the history of the Earth. So one of the most important principles in geology is understanding what's called the principle of uniformitarianism, which pretty much says that the world works the way the world works. And things have not changed significantly since the beginning of time. And this principle, while it sounds fairly simple, did not come about until James Hutton in the late 1700s. So it took a long time to kind of realize, oh yeah, if things work slowly today, then probably they've always worked slowly. And so you can see the nice little illustration that I took off of a slide share. And what process Hutton went through to make this stunning realization that, in hindsight, really doesn't seem that difficult. But the application of uniformitarianism, the application of saying, I can see this happening today in the world. Thus, if I see a fossil or I see a rock that indicates that same thing, it formed the same way. And that's called actualism. So we have uniformitarianism that says things happen now the way they happened in the past. And then actualism, which says if I see something from the past, I can look at an analog from the present to say how it formed. And both of these ideas will be important as we move on in the historical geology course. And we see here a nice little image. This is from the textbook on the left of an actual sand dune. This is still sand in a modern setting, or sorry, ripples rather than dunes, little micro dunes as they were. So modern ripples on the left and rock ripples, fossilized ripples on the right, where the sand has actually been hardened into a sedimentary rock. So the modern environment and the ancient environment functioned in the same way. Now, one thing that's very important to understand, and again, we'll look into this more next week, is that minerals are the building blocks for most of what we see on the surface of the Earth, the Earth itself. Minerals are naturally occurring inorganic solids with a definite structure and composition. And in the analogy that I've put together here, they're kind of like a Hershey's Kiss, right? You get the milk chocolate, and it's the solid milk chocolate all the way through. One texture, one composition. This would be a mineral. Whereas a rock is two or more minerals that have interlocking components. It is an entity that is built of two or more different components. So that would be analogous to the Hershey almond, where sure you got your milk chocolate, but it's not uniformly milk chocolate throughout. You get that almond in there. And so that would be like a rock. Whereas an outcrop or an exposure is the rocky surface that's been exposed. Many, dare say nearly all, rocks are formed under the surface, and it takes time for them to rise up or for the surface to weather away and for these rocks to be exposed. But when we do see them, we call that an outcrop or an exposure. And we have three basic types of rocks because what scientists like to do is put things into categories, and so we have with rocks. And we've come up with three fairly arbitrary categories. Igneous rocks are those that form from cooling of molten material, whether this is magma beneath the surface or lava on the surface, doesn't matter. If you have molten material that cools down to form a rock, you have an igneous rock. And so you can see on the image on the right, you have the molten material underlying, there's still lava under there, but on the top and all around it, you see that black basaltic rock. Sedimentary rocks are formed from particles either of other rocks or from things in the area like shells. And when they become hardened, cemented together, or compacted together, they become solid. So they form from the weathering, the breaking down of other rocks or materials, and the erosion, the moving of these materials into different places where they then get deposited or put down, packed enough, like taking that little bits of white bread that you've plucked off, putting it in your hand and squeezing it together, you can have a sedimentary amalgam of your Wonder Bread there. And we're going to spend more time next week on igneous and sedimentary rocks, as well as their partner, metamorphic rocks, which are formed when high temperature and or pressure alters and physically and chemically changes a rock from one sort to another. And so we can see on the left of the picture on the bottom there, a granite that's an igneous rock, and the exact same rock, after it's been subjected to extreme heat and pressure, gets aligned up and physically and chemically altered and is now a new rock. It's now a gneiss, and that's the image on the right. So those are the three basic rock types, and we're going to look into them a little bit more next week. It's important to understand that the Earth is not uniform. Not only is the surface different, but once you get below the surface, there are different layers that comprise the Earth. You have the crust, which is really just a very thin veneer. Oftentimes you'll see a model where the Earth is analogous to an egg. And you have the yolk in the middle, and that's like the core, which if you notice from that solid core, it's only about 1,200 kilometers thick. It's not very much. It's only about 2% of the entire Earth's mass. Most of the Earth is the mantle, that semi-molten sort of plastic middle portion, which is sort of like the white or the clear part of the egg, and makes up most of the egg's volume, and in this case of the Earth, makes up most of the Earth's mass and volume, almost 90%. And then the crust, the part that we live on, the only part that we ever actually see, is really just this thin veneer. In the egg analogy, it's usually the shell, but really the closer analog would be the membrane beneath the shell that holds all the egg innards in place. Extremely thin, and as you can see in the diagram there, only 0.5% of the Earth's mass is in this crust. So most of what we see is just a teeny tiny little fraction of what the Earth really is. And when we look at those lower levels, we break down into the lithosphere and the asthenosphere. Now, the lithosphere literally means rock portion, but it's actually the crust and the uppermost portion of the mantle. That's the lithosphere. And then the asthenosphere is the lower portion of the mantle. And this is going to be important in about 2-3 weeks when we look at tectonic processes and how the continents are able to move around. You'll want to come back and think about this image. So plate tectonics, again, is the movement of the portions of the crust, the different plates, which are made of different types of material. And when we see the crust, it's pretty much made of ocean and continent. It's made of oceanic crust, which is mafic, which is a composition of igneous rock and is very dense, and continental crust, which is made mostly of felsic rock and is much less dense. And it's this density difference that's really going to drive the motion on the surface of the Earth. And so, again, you're going to want to come back and think about this in a couple of weeks when we look at plate tectonics. And probably most of you know that the Earth's crust is divided up into a series of plates, and depending on who you ask, there are different numbers, but there are 9 big major plates. And these plates come together or pull apart at different boundaries. And some of them are spreading centers, like what we have in the middle of the Atlantic Ocean at the mid-ocean rift. Some of these form trenches at boundaries where they collide with one another, and this is where crust can actually get destroyed and recycled down as it is pulled towards the mantle. And all of this is driven by convection, an extremely important process, not only in plate tectonics and how the continents move, but in how oceans circulate and in how air moves around in the atmosphere. So a very important process. And as we look at convection, yes, I did find an amazing animated GIF of a lava lamp. Lava lamps are perhaps one of the best analogs of convection anywhere. But we have the material heated deep in the asthenosphere that rises up, displaces the cooler, denser material, and as that material cools and condenses, it sinks back down. And that's how we get the movement of the lava in the lava lamp, the wax in there. And it's how the convection in the mantle is driven. So a very important process. Feel free to tell your partners or loved ones, parents, whomever, that you need a lava lamp, so that you can stare at it to understand this very important geologic principle. Subduction zones. This is, again, the areas where the trenches are formed. You can see on the the right-hand portion of this image, you get the ocean meeting up with the continent, and because the oceanic crust is denser, it gets forced down below, and we'll tend to get volcanoes forming in this area. Generally, they're going to be on the right-hand side under the subduction rather than what we see here, but this is really because you have 2 subduction zones. We have the ocean meeting the continent over here, but we also have ocean, this would be older, denser ocean, being subducted under younger, less dense ocean, forming these volcanoes. And so sometimes you'll hear this referred to as slab pull or plate push. What is driving this circular motion? Is it that the spreading ridges are pulling apart, or is it that the subduction zones are pulling this under? And it's probably a bit of both, but this is showing the slab pull down at the subduction zone, forming the series of volcanoes on the continent. Spreading zones, you see it here, and we see the subduction again over on this side. We get convection in the mantle that helps drive this motion, this convection, just like the lava lamp. We get the spreading zone. This is analogous to what's happening in the middle of the Atlantic Ocean at the mid-ocean rift. You get this spreading apart. So we get the pull here, we get the push here, we get the slab coming underneath. And this is sort of a, 3-minute overview of all of plate tectonics, which is, of course, far more complex than this, but you get just the hint of it from these diagrams. So extraordinarily brief overview, but there you have chapter 1 and